work I've been working on forever with Zachariah Chaco, Rashmi Mishra, and Simone Rakelme at the University of Maryland. But I think it's dangerously close to being completed. And seeing as today is Halloween, I brought candy. But I also have to give this to kids who come to my door, so don't take it all. And what's Halloween all about? If there's anything worthwhile about Halloween, it's a time for taking a look at what might frighten us and then finding out that it's maybe not as scary as we thought. And so in that vein, I want to talk about Lorentz Violation, which is something that we've been taught from an early age to be terrified of. But maybe we should, maybe we shouldn't. So Lorentz Violation is not always very understood. If you remember the whole excitement with the opera measurement where they found neutrinos were traveling faster than light, and later they found that they weren't. There were things hidden on about that, including on the internet. Jokes were made, etc., etc. But not even all the jokes were understood. And so we need to make sure that when we're talking about things like Lorentz Violation, we're careful in how we communicate so that the average person or even the average scientist can understand what's going on and understands the punchline of what we're trying to say. Okay? So, why would we do such a thing? Why would we consider violating Lorentz symmetry? Well, we don't have a complete theory of gravity and quantum mechanics. And when we put them together in kind of their strong regimes, we seem to get different kinds of paradoxes or conflicts, contradictions. And so it may be that we have to give up on some fundamental assumption or another. And ideally, as this is physics, that we should find out which assumptions we should check or give up based on experiment. Okay? And so we'll think about Lorentz violation, or Lorentz symmetry. But we want to do that, think about its violation in a very sensible way. There are sometimes you hear about these really, really strong bounds on the violation of Lorentz symmetry, and you look closely at those bounds, they're actually really strong bounds on violation of rotational symmetry. And so, while that is true, that is less exciting. Maybe for some reason we feel that rotational invariance and conservation of angular momentum is more fundamental in some way than other parts of Lorentz symmetry. So what I'll focus on today is a motivated subset, let's say, of ways you could violate Lorentz symmetry, but these ways all preserve rotational invariance and they preserve CGT. So kind of the minimal damage perhaps you could do to Lorentz symmetry. Within that motivated subset, there are still two different kind of classes of bounds. There are bounds that you get from the purely gravitational sector, which in general are not so tight. As we'll see, we'll look at how tight they are. And then there are bounds that come from the matter sector, which are very much tight. They're very quite tight. Very quite tight? They're quite tight. But which of these are fundamental, is the question. You can imagine, if you're somewhat motivated by this meshing of quantum mechanics and gravity, that perhaps if the Lorentz violation is somehow tied to this gravitational sector, that they might be the more fundamental of the bounds. Okay. And they just happen to be also the much weaker set of bounds. So it could be, maybe, right, that there's some reason then why you'd be more interested in these weaker sets. However, kind of generic quantum effects quickly transfer the Lorentz violation in the gravitational sector to the matter sector, which seems to put them on equal footing, and then we don't care that one set of bounds is just, weaker than the other. Unless you can explain that difference in some way. So maybe there is some reason why the matter sector appears much more Lorentz symmetric than a gravitational sector. And that's what we'll be investigating today. The punchline, in case you have to leave early, is that we're going to construct a model, a specific model with direct Lorentz violation in the gravitational sector. However, the corrections, quantum corrections from the gravity to the standard model will be suppressed, or at least Lorentz violating corrections. And then this will give us a framework to think about Lorentz violating extensions of the standard model that are consistent with the data that we have, the measurements that we take. So how are we going to violate Lorentz symmetry? We're going to consider what's called a preferred frame, that there's some direction in space that is special, or in space-time rather. So we're going to fill space-time with an ether, which I know you all thought was done away with some time ago, but it's back. And if you can think of this this ether field at some scale lambda Lorentz violation, lambda LV, perhaps close to the Planck scale, getting a time-like Vev, then that a vacuum expectation value, then that's going to break Lorentz symmetry for us, but it will preserve the rotational symmetries. And some of the kind of in-your-face experimental results of this happening is that from Goldstone's theorem with the spontaneous breaking of the Lorentz symmetry, we should get massless degrees of freedom for each broken generator. So in this case, 3 degrees of freedom, 1 for each boost generator. Okay? Now, some of you may be worrying in the back of your minds, is this even possible? What are you doing with this breaking of the Lorentz symmetry? Perhaps you're worried about the tectonic telephone issue, that you could send a signal to some rocket ships moving quite fast, and they could send something back, and since you can send signals outside the light cone, maybe they can get a signal back before you send the signal out, which would be troublesome. Okay. However, this is not an issue, because in what we're doing, space-time is much more like a solid. If you remember, maybe you don't remember, but the reason why you can play this trick in saying that things are acausal if they go faster than light, in, say, special relativity, is that there's a complete equivalence between your frame here and the rocket's frame here. There's nothing that distinguishes them. Okay? And it's because of that being able to boost from one frame to the other with no physical effects that you get this problem, this contradiction. However, there are different types of frames here when I have this ether field. There's one in which, if you like, the ether is at rest. Some preferred frame set up by the ether. And in that preferred frame, well, causality is obvious. It may be that you have modes that travel faster than light, but they travel forward in time. So that kind of defines for you some new kind of causal structure. But the key thing here is, unlike kind of the space-time of special relativity, where all constant velocity frames are equivalent, this structure can be shown to be a frame-independent geometrical feature of this space-time with the ether. So while you can move to a different frame, there's nothing that would tell you that this frame is equivalent. Things could be quite different in that frame. Maybe much more complicated, but it should give you the same type of effects. Okay? So that's kind of the hand-waviness. But here's the Lagrangianness, or the actionness, if you like that better, of what we're going to do. We use something called the Einstein ether theory, which was written down by Jacobson and Mattingly back in 2001. And what it simply does is you start with good old Einsteinian gravity. You add some ether field, U here, some kinetic term. And this kinetic term, you can see, is not the usual one because we're violating Lorentz symmetry. And we're going to constrain it to get a time-like unit Vev, okay, at some scale. Okay. So what's nice about this theory? It preserves diffeomorphism invariance, kind of the gauge structure of gravity, so we still have that. It's going to preserve rotational symmetry when the ether gets a Vev. And it's also parametrizing with these guys the leading two-derivative effect of such a theory. So this is going to be low-energy effective theory of Lorentz violation, or spontaneous Lorentz violation, this kind of model. So that sounds like what we want to do to get an idea of what's possible, what kind of bounds exist.
So what determines the scale at which the Lorentz symmetry is broken? Is there a normalization going on?
Yeah. So I'm writing this down as it was conceived in the minds of these authors. But later we'll say, because we're not gravity people, we're particle people, let's canonically normalize everything, and the scales become much more apparent. So as I promised, when you break Lorentz symmetry in this way, you should get some new degrees of freedom, and indeed you do. It turns out that these 3 Goldstone modes are organized into a massless vector, so a spin 1 mode and also a spin 0 mode. And as a kind of previewed for you, the speeds of these waves don't have to be equal to light. You can look at the kind of the wave speeds of these vector scalar and even the tensor mode, which is also potentially different from light. They depend on these C parameters, and they can be bigger than 1 or smaller than 1, depending on what you choose the C's to be.
So is accounting of Goldstone modes obvious? Because when you have space-time symmetries,
it is obvious if you look at the structure. So perhaps you're thinking about breaking conformal symmetry down to Poincare, and you get just kind of one unique degree of freedom.
yeah.
Right. So that comes from the, if you like it, the algebra, and the way that the special conformal generators are related to the scalar invariance generator. And there's no such funny business going on here. So you really just get the normal three. So yeah, that subtlety could have happened, but it didn't, which is nice.
And actually, I mean, I agree that this theory has 3 Goldstones, but in general, it doesn't follow from the symmetry breaking pattern, because in the ghost condensate, you just have 1 degree of freedom. That's actually the minimal one. So it's true in this theory that you've chosen, but there's actually a theory that also has the same symmetry breaking pattern, it just has a single Goldstone. But that's off the topic. But
Yeah, maybe we
in
can.
this theory, everything you're saying is true, so it's okay.
All right. Yeah, I'm interested to figure out why
Yeah.
that statement in this conversation. Good. Yeah. So one kind of fun bound you can think about now, since we're living in a wonderful world of gravitational wave astronomy, as we've started to measure some of these tensor modes. A little bit, you can ask, hey, are these constrained by LIGO? The answer is yes, but not very much. So we've measured the speed of gravity, but it won't be the leading effect that we're going to see here. But it's kind of fun to see that it's now joined the game of ways you can address these theories. Okay, so what I've hoped I've done so far is just kind of set up the fact, or the idea perhaps, that this Einstein ether model isn't crazy, that it's somewhat sensible and somewhat general, low energy effective theory of ways you can break Lorentz symmetry. And so as a theory it's self-consistent, but as I said earlier, we care about how it meshes with experiments. So what kind of checks remain? And so we'll look at different tests of this model in the gravitational and the matter cycle, and see what kind of bounds there are. The first of which are so-called gravitational Schrenk-Log bounds. As you may or may not remember, if you have some particle traveling quite fast, say a particle emitted from some kind of fission reactor, if it's a charged particle, electric charge that is, it's traveling through a dielectric medium faster than the phase velocity of light in that medium, then it will emit light until it drops below that speed of light in the medium. So this is a fission reactor core glowing blue because it has particles flying out from it faster than the speed of light in water, and emitting, as we see it in the blue spectrum, as they slow down. Now, suppose we were in this Einstein ether theory, and we had some particle that was charged under gravity, which is a particle, right? Everyone's charged under gravity. And suppose it could go faster than the speed of gravity, or faster than the speed of these ether modes. Then it would radiate in either gravity or in the ether until it had dropped to the speed of the ether or the speed of gravity. And since we've seen very, very energetic cosmic rays going essentially the speed of light, traveling for a long time, or long distances through space, the bound is basically that the speed of gravity or the speed of the ether has to be greater than or equal to light. So while we were, interestingly, we're driven by experiment to only consider gravity and ether speeds that are faster than light or equal to light, but not slower.
So when you say gravity / ether, I mean, is the correct speed the speed of the spin 2 excitations? The phase velocity of the spin 2 excitations? Is that the velocity you should be comparing to for this?
I don't think it's just the spin 2. I think that the other modes also ways you could radiate kind of energy away from the particle as well.
And you don't care because you're not detecting the radiation, you're just looking for the energy loss, so you
That's
don't
right.
care.
That's right.
I see.
Yeah.
Okay. Has this calculation been done? I mean, is it actually, it's kind of, you can think of it as a decay rate, right?
Exactly. Yeah.
So it's been done in
Yes.
this theory?
Yeah. People like Ted Jacobson and compatriots have looked into this. A lot of these things have been collected. Next set of bounds are the so-called PBN bounds. And what is PBN? It's just parameterized post-Newtonian. This is a set of coefficients, these PBN coefficients, for encapsulating how your favorite theory of gravity differs from Newtonian gravity. So there's some specific values, for instance, for general relativity, but in general, any generic extension of Newtonian gravity has its set of coefficients. Okay? The ones that we'll care about in this Einstein ether type of model are the so-called alpha coefficients, alpha 1 and 2, because they kind of are set by preferred frame effects, and that's what we've introduced. Every other coefficient in Einstein ether is exactly equal to GR. So there's only ones that could be different. People have calculated what exactly these coefficients are for the Einstein ether theory, and it turns out for small C parameters, which are the ones we're interested in, that basically the alphas scale like C. So if we found some bound on the size of an alpha, then that's also setting a bound on the size of the C's. I'll tell you, and if you read these papers, they will tell you as well, that there does exist a kind of 2-parameter family of choices of these C values that set these alphas to 0 exactly. However, that certainly doesn't seem generic, and it doesn't seem stable under quantum corrections. So if you were to set them equal to that, it's not clear that they would stay close to that value. So we will take the more generic, untuned choice, if you like, that they just scale like the C's. So what are the bounds then? Alpha 1 must be smaller than 10 to the minus 4, and alpha 2 smaller than 10 to the minus 9. So yes.
So I should have asked this before. Can you go back before when you were talking about this? Yeah, this Cherenkov bound.
Mm-hmm.
So since I can think of it as a decay, right? And so if I think about it that way, then the decay rate should be suppressed both by the fact that there's somehow the coupling is Planckian to gravity, I would guess, but also the phase space is small, right? If these differences between the speed of lights are small, then somehow this lifetime gets very large. So shouldn't there be some bound? So it should shouldn't it allow say the gravity or the ether waves to be just a tiny bit?
Yes.
But that's so small that it's not interesting compared to other because there's other small numbers in your band, right? You're saying that's not interesting. That's not an interesting region allowed.
Yeah, not really. If you go back and look at some of these guys, whether or not these are faster or slower than light doesn't depend on the magnitude of these things, just on kind of the ratios. And so we're more interested in the magnitude, in a certain sense, of these guys.
I see. Yeah.
And so this becomes the more interesting effect for us.
Okay, so I forgot that. You're right. So to get the vector and scalar modes close to the speed of light is some total accident. There's nothing special about that.
That's right.
Okay.
But yeah, so it is kind of a constraint on the space, but it's not the most interesting.
Okay.
Good. All right. So what do these alphas mean for us? Going back to Jack's question, what are the scales involved? Give me some physics here, right? So how big do we expect these CIs to be? So to get a handle on that, we're going to rewrite our action in a canonical normalization, where we just introduce a big field U, which is our old dimensionless U multiplied by this scale of Lorentz Violation. So that when this thing gets a VEV, its VEV is at that scale, Lorentz Violation. Okay. So this becomes our new rewritten action in terms of these guys with this new kinetic term. And what you see then, since you have this suppression by Lorentz Violating scale here, that then the natural size for these CIs is to be set by kind of the difference between, or the ratio, the square ratio of the Lorentz Violating scale to the Planck scale. Except in the case of C4, which is got a couple extra factors of U involved, which is additionally suppressed. So then what these PPN constraints would imply then is that Lorentz Violating scale has to be, at least somewhat, several orders of magnitude below the Planck scale. There's some suppression or some reduction in these scales. Okay.
And with these C's, the C's of this order, then the various speeds are of order 1, is that right? They're not small? All the speeds are order 1.
Yeah, they're order 1.
So why do you, except for the tensor. The tensor would still
Tensor will be close to 1,
close to 1, but the others could be anything, so
but order 1.
or order.
Okay, so that's it for gravity. I should say there are other bounds that exist, but these are the leading guys. But the bounds on standard model Lorentz Violation are much tighter for the very simple reason that you can look at something like a photon or an electron for a long time and just keep measuring it to see how much is violating Lorentz symmetry and keep seeing that it's not very much. Okay? So these are going to be orders and orders of magnitude more stringent. And the tightest of these bounds come from basically a modified dispersion relation. And instead of just having, E squared is P squared plus M squared, that there's some additional dependence on P squared going on that's changing this. Okay. So if you like, this is somehow corrections to a two-point function. It's the propagation of particles. So it's not even at an interaction level that they're. So let's start with the photon. We want to get the leading bounds. We want to write down the operator of lowest dimension, and we want to preserve gauge invariance. And we also want to make sure that there are an even number of insertions of the ether field. And the even number is so that we can preserve CPT. Okay? It's just this connection. If you have an even number of ether guys, then you get a CPT preserving Lorentz Violating operator. So this is that operator right here. Okay, so we parameterize the size by some kappa gamma. And then there are actually two different processes which are forbidden if you have Lorentz symmetry, but which open up once you have this operator. And just the spontaneous radiation of the gamma in vacuum, and also the spontaneous decay of gamma in vacuum too. Okay. So these, depending on the sign of kappa, one of these guys will turn on. They're both independently bounded, and so you get this two-sided bound on kappa, which, to be kind to ourselves, let's take the weakest of them to say that there's only 16 orders of magnitude between these two scales when you take the kind of naive realization of this model.
So both are forbidden by LS dispersion relations? What does that mean?
Lorentz symmetric, sorry.
Okay, read. Right.
Binormal. Okay. So you can get similar bounds looking at matter. If you look at kind of the interactions of the fermions in the ether field, the lowest dimension gauge invariant operator you can write down would be this, which gives a constraint very similar to the photon bounds. The take-home lesson being that these kappa parameters for standard model fields have to be much, much smaller than the C's. The C's are still set by this separation of scales. But then these kappas have to be additionally much, much smaller than the C's were constrained to be. You can imagine the C's were small, but...
So your rule here for coupling the thing to the matter fields is to use the canonically normalized fields and then just suppress in your ether sector and then normalize things by lambda LV with a coefficient of order 1? Is that how you're getting these?
Yes, that's right.
Okay.
To go back on transparency for a moment, is there an FF dual possibility?
Yes. I think so, but I don't think that change. I think you're not going to get anything a very tight bound there. And so I see no reason why these could couple to FF dual, but I don't think that's going to be the leading.
It would just be a big parameter for PVD.
Yeah, that could be, yeah.
Okay, so what if we were doing the naive thing, like QFT1 thing, and just set these kappas to 0? So if we don't like them, 0 they be. Well, of course, that's not going to do us any good because radiative corrections from the gravitational sector will change what we set them at true level. Right? So, in particular, we could look at the photon and say I have some graviton loop that's correcting its propagation, and put in 2 insertions of the ether bev, and I'll get some correction then to the 0 I put in. That's of order, a loop factor over 16 pi squared, and then the scale, Lorentz Violation will be one scale. Okay. So, if we took these to be of the same order, Lorentz Violation and Planck, or even if we took the gravitational bound, this difference of 10 to the minus 9 between them, such a correction is in gross conflict with the experimental bounds. Okay? So we cannot just use the Einstein theory as is if you want to talk about the real matter sector that we measure.
So when you say you had bounds on the kappas,
Right.
this bound is measured like 10 to the minus 20 and quite a little bit. So how do I know it's in gross conflict?
So if you took this, right, this is the best possible situation perhaps, this would be something like 10 to the minus 9, so this is something like 10 to the minus 11.
Right.
But we saw before I needed this to be smaller than 10 to the minus 16.
Okay, that's the number I should
Yeah.
be remembering. All right, okay.
You're stopped by 5 orders of magnitude, but we worry about such things. So what's the game? You could suppose perhaps there's some mechanism that would suppress this communication of Lorentz violation. So that if you started off with these kappas equal to 0, there's no explicit Lorentz violation in the standard model sector, that its communication from gravity was suppressed in some way. Okay. Then these comparatively weak bounds in the gravitational sector would be the leading bounds on your model, on your framework. And the way we were going to consider doing that is using some kind of strong dynamics. And this is kind of how it would work. You can imagine that you have somewhere in the UV a strongly coupled CFT, which then scales closer to us as spontaneously broken, so that we're living in a non-conformal life that we observe around us. So you have this CFT up here, and it couples to gravity, and it's that gravity that feels this Lorentz violation. Then if we make the assumption that the CFT operators that are sourced by this Lorentz violating gravity are irrelevant at low energies, then the strong coupling means that as you go to lower and lower energy scales, these quickly flow away. And so when you look at low energy states, everything looks very Lorentz symmetric to a high degree. This is the cartoon. So down here, our standard model states would be some kind of composites of the CFT below this breaking scale. And here we have this apparently Lorentz symmetric world around us. And as you probably agree, the cartoon looks great at the level of PowerPoint cartoons. But it's hard to verify by direct calculation because we're using a very strongly coupled quantum field theory and perturbative techniques break down. So how can we check this qualitative picture to see that it actually checks out? And how we'll do that is through the ADS-CFT correspondence. ADS-CFT relates strongly coupled conformal 4D gravity or 4D theories that we are interested in, 4D theories without gravity, to weakly coupled 5D theories in anti-acidic space. And so gravity, as well as non-trivial background, non-trivial geometry, gravity is an important part of the game. In particular, if you look at a so-called brane truncated slice of ADS, then this is interpreted as being dual to some strongly coupled theory with a nearly conformal phase that breaks below some scale. So these warped geometries with this warped extra dimension have a metric kind of like this, where you have slices of Minkowski space that are getting stretched, if you like, as you go to the UV. These warped extra dimensions are a geometric way of separating scales. This is, of course, the game that was played by Randall and Sundrum to get a natural separation of scales between the Planck scale and the electroweak scale. And so we'll be using the very same type of setup to make our model go through. So to remind you of kind of how the holographic dictionary goes, when we're talking about this, the CFT cutoff, it's like talking about the UV brane in a Randall-Sundrum scenario, where you have two branes and you have some warped geometry that links the two. The symmetry breaking scale in the CFT is related to the IR brane. The way you get between those scales is, of course, through a normalization group flow, parameterized by some u typically, and that's dual to this warped extra-dimensional parameter theta, which stands between the two branes. If I'm talking about an elementary field in my CFT, that's one that lives on or near the UV brane, and a composite field is one that lives on or near the IR brane. So then you can see the natural way to try to get at the model we're interested in. We can take our Einstein theory and stick it on the UV brane. We can take the standard model and stick it here in the IR. And then the way that Lorentz violation is communicated from the UV to the IR is simply through the bulk gravitational interactions.
So goldstones don't propagate in the bulk?
The goldstones of the ether?
Yeah.
They do. They source the kind of, if you like, the gravity degrees of freedom. You know, the metric has got lots of pieces in it. It'll source the scalar and vector modes, so they can.
But they're not actually propagating in the bulk, right? There's not a.
Oh, right.
That's
Yeah.
what
Okay.
you're
You're,
asking.
yes. So yes, the ether is confined to here, but you'll have consequences of the scalar and vector modes that are communicated to here through the metric. Okay. Good. So we went to the trouble of taking our 4D theory and going up to the 5D theory. We'll now take the trouble of taking our 5D theory and going to a 4D effective theory. So that we can make sure we're, for clarity of understanding, that's right, why you use effective field theories, right? As was just mentioned, we're only going to have 5D gravity in the bulk, which is nice. And at energies below the scale of this extra dimension, or Kaluza-Klein scale, KK scale, in our effective theory, only these so-called zero modes are present, modes that have no mass, massless modes. Now you might worry about the other states, the Kaluza-Klein states, because they tend to have large overlap with standard model fields, and presumably then they could contribute quite a lot to the Lorentz violation in the standard model. However, for the same reason that they have a large overlap with standard model, they have a small overlap with the UV, and so their actual feeling of the Lorentz violation is quite small. And we'll see explicitly later that their communication of the Lorentz violation is suppressed. So then the low energy fields, the things that we care about in our EFT to try to gauge whether or not we're succeeding or not, screening the standard model from Lorentz violation, are going to be standard model fields, ones that live on the IR brane, the normal graviton that we know and love, these three Goldstone bosons, or Goldstone modes, And a new field, the radion, which is called the Lorentz scalar here, it's a scalar mode that's associated with kind of the fluctuations of this extra dimension. And so in the low energy theory, that scalar mode shows that. Yes?
How do you stabilize the size of the extra
In whatever favorite way you'd like to, but we're gonna let the radion be massless now. But yeah, it should be pretty calculated. Okay, so the first, going back to bounds then, the first statement basically is that all of the gravitational bounds we had on our 4D Einstein theory will transfer directly to our 4D EFT. We've basically gone to low energy probes, low energy states, so that basically we cannot distinguish that there is a bulk. We're only looking at these very long wavelength probes. They feel the UV brain just as close as the IR, and so we have exactly the same bounds on the Einstein theory, the gravitational section, in these low energy states. Okay? Modulo the fact that our massless radion and our massless scalar mode mix, those are both scalars, gravity scalars. So there's something interesting going on there, and we'll return to that later. But essentially, all of the bounds we saw before on these alpha parameters just carry right over. So nothing about that scalar changes. However, and this was the whole point, right? The communication of Lorentz violation from gravity to the standard model is greatly modified. And why is that? Remember that we're looking at these constraints on modified dispersion relations, and we have pictures like this in our mind. So we're inserting webs of the ether. But now if we want to do that, these legs have to go through the entire extra dimension and back to correct at least the parts that have the Lorentz violation. Okay? So our loops have to traverse the entire bulk to get anywhere. And this will do some nice things for us. It means that when we estimate what these diagrams are, we don't let the... Okay, so this is just the same thing we did before in our EFT. We have this new parameter where we're coupling these guys together with some kappa gamma. Two instances again for CPT. But crucially, this loop is now cut off at the KK scale. Okay. That's where our EFT is done. You can't let it go any further than that. And so then we get a much suppressed kappa gamma, if you will, relative to what we saw before. It's suppressed by mkk squared over m Planck squared, which presumably could be quite small and give us the necessary orders of magnitude that we need, so that this is way below or sufficiently below the experimental bounds.
So,
Why is that diagram divergent?
Why is it divergent?
Looks convergent to me.
see, you don't have any fields in the bulk except for gravity. So is that right? So in general, you would have, so all the other modes are really heavy. So that makes, I'm trying to go back to the CFT, there's a 4D CFT interpretation of this setup, right? And there what you would say is that, and you actually said it earlier, you said that, well, you have these operators that violate Lorentz invariance in your CFT, but they're very high dimension, right? And that's sort of clear that would then suppress their effects at low energies, right? So here, you've taken that to an extreme. You put in nothing into the bulk except gravity, so the only operator in your CFT that you're worrying about is TU nu, okay? But then I'm having a hard time seeing why you have any effect left. See, I would have thought that in the limit when all these operators go to, because you're saying that there's some effect of Lorentz violation that's left, even when I take all the operators in the CFT that carry, that get a, that are turned on, that have Lorentz violation, you're taking all of their dimension to infinity, then you're still getting some effect that's left over, and I find
Well, there are these extra modes still in the bulk. So
the only thing he has in the bulk is gravity.
Yeah.
He only has gravity in the bulk.
So I think,
So this just looks funny to me. I mean,
right, well, I mean, I don't know if this is helpful or not, but this, in a sense, is a higher dimension operator, right? It's really dimension 6 in a certain sense. So maybe this is something like.
this is now an effect that you're trying to compute, right? This is an effective operator in the low energy theory below the Decay scale, so you're trying to compute it. It's not.
Right.
I guess I don't understand in the sort of CFT picture where this effect is coming from at all. When you tell me you did this higher dimensional diagram and this is what you got,
Yeah.
I don't know. This is the only check I can make is, does your answer have a sensible CFT interpretation? And I just can't, I don't understand what it is.
Dimension 4 operator that couples gravity.
Right.
To the CFT.
So I think the answer is that we can't get rid of T mu in a certain sense.
I'm sorry, could you repeat that
It's giving
explanation?
a dimension 4 operator that couples gravity to the CFT. Which is the kinetic term of the new field.
It's the coupling of the graviton to the stress tensor of the ether theory. Right?
Yeah.
Yeah.
Okay. Okay.
Going back to the divergence of this diagram, it's certainly divergent if you don't have the instances of the ether.
Yeah, but with those insertions, just make it convergent.
Yeah, I mean, it is, I guess, in a certain sense, except for the scales.
I mean, I don't think it's, I don't think he's saying, maybe there's a difference of language, because I don't think Chris is really saying it's divergent. That first thing there is saying that essentially that it's cut off at the KK mass scale. And that is what the extra dimension is doing for you. It's giving you a finite result, but roughly the size is as, as is written, that what you would write in the 4D effective theory is softened at the KK scale. That's exactly the effect of the extra dimension. I think you guys agree. And then it just turns into that thing there because of the identification of what the Lorentz Violating scale is. I think kappa just involves the definition of kappa involves lambda LV,
That's right.
right?
Yeah.
The real size is just the thing given on the left. Lambda LV is not real. It's the scale of gravity of violation in the gravity sector. Right? So the second thing is just so you can compare the size in the gravity sector and the matter sector of the Lorentz violation. I think I understand now my question, so I just want you to know that I'm now happy.
Okay.
Okay?
Have some more time.
I'll have some more candy, thank you.
Okay, good. All right, so we've made some claims of kind of victory based on things getting cut off at the KK scale, so let's make sure that that's true. So we'll digress briefly to look at the full, this is not the EFT, this is the full 5D gravitational two-point function, so we can believe our EFT analysis, to make sure that things behave the right way. So if you consider the full 5D action, right, we just have gravity and cosmological constant, and then we have two branes, the UV and the IR that we're calling them. And these guys have some Lagrangians of different fields that might be on them, and some so-called tensions. And the standard RS solution is the classical background solution here, where you get the metric that we saw before in some relationship between the curvature, K, and the ADS space, the 5D cosmological constant, and the tensions on these branes. Okay? So that's kind of old news that all goes through, but the important thing is then we get this equation of motion for the fluctuations of the metric, okay? Which is the standard equation of motion we've got before without any kind of Lorentz violation being denoted here in green, and then some source terms on the brane that are going to tell you how how it responds to these things. Okay? You proceed by kind of your standard Green's function method of analysis. A little wrinkle on this one is that where before you could have chosen the so-called RS gauge and all of the metric fluctuations would have behaved the same way in the equations of motion. Here, there's these slight differences for these scalar, vector, and tensor modes because of the ether on the UV brane. So we can write down at least kind of the formal solution for what H is in terms of the source terms and the Green's function. Okay. For the H field, which of course satisfies the typical Green's function equation with these boundary conditions. And the significant thing here is that on the UV brane, we have something that encapsulates all of the Lorentz violation on the UV brane. It's these guys that are different for the scalar, vector, and tensor modes. And then, of course, you have these different Green's functions for each of those modes. Once we have that full two-point function in hand, we can check to make sure that our EFT has done the job we hoped it would do. So remember, we're interested in these traversals from the IR brane all the way to the UV brane, to the legs of this propagator. So we can take our Green's function and stick one of the legs, if you like, one end of it on the IR brane at theta is equal to pi, and then just look at the leading behavior in kind of a momentum over the curvature scale at what's happening in our Green's function. And what you can see here, these green guys showing up, also nice and obvious, is that in these gravitational modes, the leading order behavior, these zero modes, if you like, have kind of order 1 Lorentz violation. These are these big changes to the dispersion relations that we saw, these C parameters coming in. In fact, you did check that looking at this, you recover exactly the dispersion relations you got in the Einstein theory that you get in the 4D EFT here. With the wrinkle of you have to deal with the mixing of the radion and the scalar. Okay, so that seems to check out. How about above the KK scale? This is really what we're interested in. If we go above the KK scale, this is the leading order piece of the two-point function. And you see that as theta differs from pi, you get this exponential suppression here of the propagator. This is for space-like momenta. If you were to look at the time-like piece, you have the same kind of suppression from wild phases, if you like. So what does this mean? This exponential cutoff, right, of the propagation of these modes above the KK scale is what gives us this effective cutoff to our integrals in the 4D space. Okay. So this is kind of where the magic all happens.
So you're expanding just to understand what you're doing. Right now you're expanding the propagators for small, the boundary bulk propagators and small p-squared. The boundary now is the IR boundary.
Yes.
But you're going to do this loop, you have to integrate over all momentum. So
The bottom one is not for small p-squared.
So is the bottom one the large p-squared limit of the upper one? Or what?
The bottom one is
okay.
just
So,
above
sorry,
the KK
so that was
scale.
just, okay.
So the
this is
KK
part
scale
of
is
the
still
division.
small relative to, the K here is kind of standing in for something like the Planck scale. So we can still make this expansion, but instead of having our P close to 0 here, getting this pole, we're putting our P, if you like, close to the KK scale, or just above the KK scale.
So this other one is the opposite limit. You're looking at what happens when the momentum is large compared
Yes.
to the KK.
Yes, that's right.
Yeah, okay. Thank you.
So since I've been mentioning the radion, I should tell you what happens there. Especially since you may be worrying about the radion and its coupling to the standard model, which is the coupling of the scalar mode to a trace of whatever's on the IR brane, with kind of an IR scale suppressed coupling. So potentially, that sounds like it could be relative to these Planck suppressed interactions, a big source of Lorentz violation. However, just like the KK states, the radion couples a lot to the IR and not much to the UV. So actually its mixing with the scalar mode turns out to be exponentially suppressed. And so you get exactly the same type of Planck-suppressed interactions from the radion as you would have gotten as far as communicating Lorentz violation as you would get from, say, the other scale mode. There's nothing different in that story if you would look at kind of radion loops contributing to dispersion emission of a photon or something. They set the same scale of operators as these other ones.
Somehow I've lost track of why the radion does not couple at all to the ultraviolet or the suppressed matter. Just read on that.
It's localized in the IR.
I'm sorry?
It's localized in the IR.
Yeah, that's just where it likes to live. And I don't know if this helps, but imagine going to the, is this the RS2 setup, where you take the IR range to infinity, and you completely lose the radion. It's tied to the IR.
Conceptually, the radion, you can think of it as just another mode that lives on the IR brain.
Well, except it's stabilizing the whole setup, is it not?
Oh, no, that'd be, you think of maybe the Goldberg-Wise field. So the radion does not stabilize.
In this approach. Okay.
Yeah. But if we had taken the time to be complete and stabilize it, then the radion would have gotten a mass. So there's definitely an interplay there.
That's sort of what I was concerned with.
Yeah.
I mean, there's also the issue of whether the radion mixes with the bigs or not.
Right.
Which could change things, yeah. Okay.
So finally, then we can look at the final constraints on this theory, and perhaps unsurprisingly, with this mechanism in place, and depending on where you choose your IR scale to be, or the equivalent of your KK scale, then you can have different kind of effective bounds based on. Let me say this a different way. The bounds on kappa gamma turn into bounds on where the KK scale can be if you want to stay consistent with the experiment. If you're to take somehow the Lorentz violation be at the Planck scale, then your KK scale has to be no bigger than 10 to the 10 GeV. But that's, sorry, yeah. If you take the Lorentz violating scale to be suppressed, no fancy choices of the C parameters, then you can have the KK scale as high as 10 to 14 GeV and still be consistent with experimental bounds. And what's nice about this is all comfortably above the highest scale set by flavor, roughly 10 to the 8 GeV. So if you wanted to consider some Lorentz violating extension of your standard model, you could put this in kind of the back of your mind and say, I'll put this in with some KK scale at 10 to the 10 GeV or something like that, and then I can just set it and forget it to a large extent. I don't have to worry about flavor, I don't have to worry about anything else. I just have some way of having a Lorentz violation of gravity without breaking things in the standard model. So then the summary of the model is that we think of the standard model as composites of some strongly coupled quasi-conformal sector. We have gravity that is sensitive to some kind of Lorentz violation, but the graviton loops are cut off by this strong dynamics at a lower scale, IR scale. In this case, the leading signal of Lorentz violation would come from those purely gravitational effects. There would be some bounds on the indications of compositeness from colliders, but those are quite low, like at TeV scales currently. So, Lorentz symmetry doesn't have to be fundamental, but could be emergent at some low scales in the ways that we see things in the standard model. Experimental bounds are tight in the matter sector, but much less so in gravity, and we've shown you how you can screen the standard model from these gravitational Lorentz violations. And that after you've done that, satisfied gravity, your matter sector is effectively unconstrained. So what we've done is we've used strong dynamics to hide Lorentz violation, if you like, and then shown that we can estimate those effects through the ADA-CFT correspondence, and that bears out kind of our hopes or our intuition on the CFT side, giving what I think is a somewhat sane way to study Lorentz violating extensions of the standard model. Thanks.
Is there anything in very early universe history that would be sensitive to these kinds of Lorentz violating things, the universe that evolved in some kind of preferred frame, for example, as a result of this?
I think in general, yes. From what I haven't looked at this in as much detail, but there are people who think about these things a lot more than have, and I think basically what has to happen is your preferred frame has to line up with the CMB pretty well, and that the CMB kind of sets then your preferred frame. That's my understanding. Or OTCB. Oh, sorry,
Maybe a quite a related question. Since you're allowing for speed higher than speed of light, can you use the Einstein ether model to solve the horizon problem without inflation? Is it used for this kind of problem?
I don't know.
I'm just curious.
Yeah, that sounds like an interesting idea. Unfortunately, I didn't have it, so.
I want to understand your statement. You say the CMB has to line up with the preferred frame. So what do you mean by that? I mean, we have CMB coming at us from all directions.
But it's a preferred frame, right? With the
Yeah.
measure of velocity with respect to the CMB.
Yeah, well, that's true. Our
Exactly.
planetary velocity.
Exactly.
So if we
if
could
not,
go out to,
yeah.
but we have CMB being measured, on the Earth and measured at satellites, that's not enough of a separation.
Yeah, because that's not the issue. The issue is if the preferred frame set by the ether were different than the CMB would be moving in that preferred frame, and you see presumably some effect of this part's redshifted versus this part's blueshifted or something. So it would look like to us like the CMB was moving instead of being this surface, kind of a static surface. I think that's my understanding.
But I'm asking, I suppose we...
It already does look like it's moving.
Oh,
But I mean,
Because
suppose
we're on a
we-
planet and all that.
right,
So-
right.
So how do you, so what is it that you're noticing in this theory?
Well, the part that somehow the part that we're approaching is, it doesn't look, of course, relativity predicts exactly what the difference should be between.
Okay, so it won't look like a boosted.
Yeah, it would look like that.
So you can't model the lack of isotropy as a Lorentz boost.
Right.
But you suppressed all of these Lorentz violating operators to that, so probably it's not the most, it may not be the most sensitive probe, right?
Well, it's suppressed in the
Right,
current.
I mean, in other words, you've got to be able to tell that you're moving through the ether, but now you've suppressed all the couplings that matter to the ether
That's right.
by these tiny, tiny, tiny numbers.
That's right.
So any effect will be suppressed by that.
That's true.
Right?
So I'm kind of, what I was spitting back to was stuff I had read where they were looking at kind of generic Einstein ether, because they didn't know about our great work yet. Not yet out. But yeah, that's true. The CMB effects would be much reduced. Yeah.
Can you happen to know offhand what kinds of limits on the C coefficients will come from LIGO in the future? I mean, if we can observe a gravitational wave source optically and gravitationally.
Yeah, so there have been some papers on exactly that case, and there you can get some pretty non-trivial bounds. There was a little bit of a flurry of excitement when there was this kind of measure at the same time thing with Fermi, right? So I don't remember the bounds that they gave. But they were, I don't know if they're competitive with the alphas, but if they weren't, they were knocking on alphas lower in a certain sense. So they were getting to that level. I think that So if we are so lucky as to be able to say this came from a real coincident event, then I think we can say something pretty strong.
What happened to that coincidence then? That was debunked?
I think there's no compelling reason to believe that they came from the same source, other than they happen to be coincident in time. But that's the thing you want to be an output, not an input. So that was my understanding. But I mean, yes.
So, what motivated you to study Lorentz violating models? Is there something that we can get out of a Lorentz violating model that we can't get otherwise?
It's more of a question of fundamentals. At the level of, we don't, you never know something is fundamental, right? I can't say it's got to be Lorentz violation all the way down, and there have been, and though I'm not from this either, there are some realizations of kind of quantum gravity which seem like they may either accommodate or even necessitate some measure of Lorentz violation.
Okay.
And so our motivation is kind of at the very dumb level saying, when you put quantum mechanics and gravity together, you seem to get some contradictions sometimes, which may mean that you've made an incorrect assumption somewhere.
Okay.
And not knowing which assumption that is, let's check them all and see if we can. How desperately do we need the Lorentz violation? How desperately do we need unitary? Probably we really need unitary. Maybe not. I don't know. But you have to say, where do things break and how badly do they break?
But is there any reason to suppose that this kind of theory would resolve the ability to put gravity and quantum mechanics together? I mean,
Well, this is.
I guess in some sense, it's a consistent theory that does that. Is that right? Or is there still some problem?
Right. Well, so we're certainly not claiming anything about quantum gravity. So we're using the Einstein ether, which is kind of this low energy EFT in a certain sense of its gravitational Lorentz violation. But so what we're saying is, if for some reason you had some, UV complete quantum gravity that violated Lorentz symmetry, why don't we see it now? Maybe it's something like this is happening.
But that violation doesn't help the conflict in putting these two theories together?
Yeah, I'm not solving quantum gravity, unfortunately.
But there's a proposal by Verhaaren that it does, because it allows you to write a gravitational action in which you have terms that have more than two spatial derivatives, but only two time derivatives. That preserves unitarity, but it suppresses divergences so that you can get a much less divergent or possibly even a finite model.
I see.
It's not known whether, it's not clear at this point whether that kind of theory really goes free. There are all sorts of potential problems with stability, but at least it's candidate.
That was precisely what I was wondering.
I wanted Steve to answer your question. If there are no further questions, let's thank me again.